Yes, Arun, you can.
Yeah. So let's start. Good evening, everyone. So it is a great pleasure to invite Professor Nicolas Gisin, who is one of the world leader in the field of quantum information and quantum technology, and his interests cover a wide range of topics, starting from foundations of quantum mechanics to philosophy to applied, quantum communication, applied science, and quantum technology. And he has many projects, and he has received many prizes. So I don't have to list here. And he has authored more than hundreds of scientific papers in Nature and other various prestigious journals. And also, he written a popular book on quantum chance and non-locality. And he is also co-founder of this successful company, which is this ID Quantic, the first company to have commercial quantum cryptography device. So I welcome Nicolas Gisin again, and it is a great pleasure, as I said. And it was a great privilege that I visited him in 2000, and also he visited India, in 2008 when I organized this school and conference on quantum information in the Institute of Physics in 2008, and he has been visiting India very often. So, let's welcome Professor Gisin. Yeah.
Okay, so thank you very much. Welcome, everyone. Thank you for the nice introduction. Today, I will not talk so much about technology. There will be just a little bit. I will mostly be talking about more fundamental questions in quantum physics, in quantum non-locality. However, motivated, as you will see, by ongoing developments in quantum technologies and quantum communication. So the title, as you see here, is Quantum Non-Locality in Networks. One picture that you have here is this old experiment we did 13 years ago between, let me see, I put the right pointer on, between a village north of Geneva called Bellevue and another village south of Geneva called Bernay. So I think that was the kind of first Bell experiment outside a laboratory using the Swisscom telecom network. Well, so let's ask ourselves, so what are we really testing here? So of course we're testing Bell locality, local hidden variables and things like that. But how are these two particles in this case supposed to be correlated classically or locally? And if we just think in terms of two parties, there are different ways. I mean, we could really think, I mean, the historical way is the second one. That's really how John Bell used to think of it, that, there's a source, and this source, so here in the middle somewhere, actually Cornavin is the train station in Geneva. And from this source, you have particles, photons in this case, that go to Alice and Bob, as we say today. And these particles, they really carry information, they carry additional information in addition to the usual quantum state. They possibly carry something more, some additional information. That's the traditional, a bit old-fashioned way of thinking. And there's a more modern way. We just speak about shared randomness. And this shared randomness is like given by God. It's just given everywhere. And everybody, Alice, Bob, get this shared randomness. Now, if we have only two parties, Alice and Bob, then whether we use one view or the other doesn't make any difference. But now let's go to a more realistic network. And in a realistic network, we don't have just A and B, where you have A, B, C, D, and I don't know, we have many, many parties. And these parties will be connected by sources of entangled particles, but these sources might well be independent. There's no reason to think that everything is dependent. You have one source going from Alice to Bob, and then maybe another source going from Bob to Charlie, and so on. So let's make that more concrete. And this is really this independence of the sources that is going to make all the difference in my presentation today. So here is an example just of a little network. And you see you have a loop somewhere, and some parties receive free. So let's put also the sources in it. So Bob, for instance, gets connected to Alice, to Charlie, and to Fiona, and can do a joint measurement on all that and get some results, and so on for everyone. But the key point here really is this independence of the quantum state. You know, this quantum state is possibly powered by a solar energy. This quantum state is powered by nuclear energy. And it makes a lot of sense to think that these sources, to assume that these sources are independent. Now, in order to test whether this is really a quantum network with some quantumness, we should compare it with the case where these quantum states are replaced by shared randomness. Again, some shared randomness here between A and B, some shared randomness between B and C, but we are going to keep the assumption of independence. So these different shared randomness, or you may also say different local variables, are independent. We'll come more to that. And then the idea is, can one with this independent shared randomness reproduce the statistics of the quantum predictions? We can even go one step further and just say we have some kind of non-local boxes between A and B, and another non-local box between B and C, and so on. And again, we're going to assume these non-local boxes, first of all, to satisfy no signaling, as we are used to, and this is the new thing, independent. So it should be independent. Each box is independent of each other. So I call that here the NSI principle, no signaling and independence. And here's a first example, which you see is already pretty old, and which is essentially similar to entanglement swapping. So you have Alice, Bob, and Charlie. Alice and Bob, they share some quantum state, and then we replace the quantum by this local variable lambda1. And Bob and Charlie similarly with a second quantum state, or this second independent lambda1. And at the end, we get probability distribution of getting the results ABC given measurements for Alice, Bob, and Charlie that I label X, Y, Z. And this independence locality is really that the probability distribution of lambda1, lambda2 factorizes. This is really this independence assumption. And now if we make this assumption, we get that the total probability distribution now conditioned on lambda1, lambda2, there should be the probability for Alice to observe her results given her measurement input, and only lambda1 because lambda2 never reaches Alice. For Bob, it depends on lambda1 and lambda2 because he gets both variables, and Charlie, he gets only lambda2. So that's the assumption, which is quite plausible, I think, under this independence assumption. And then we would like to get Bell inequalities or Bell-like inequalities. So it's the same kind of spirit as Bell games, but under this network assumption or configuration with independent variables. So this NSI assumption that the sources are independent is very natural. And somehow I'm going to show you that this is actually already implicit in all our Bell tests. So it's not something really new. Let's look at it like that. So here I have our usual Alice and Bob. And usually Alice is, the measurements that Alice performs is provided by some quantum random number generator. I put an A here just to say that's on Alice's side. And of course, it's symmetric on Bob's side. And then you could really imagine that this quantum random number generator and Alice, they share some local variables. And these local variables really determine which input Alice is going to produce. So this is the output of our random number generator, which is of course also existing at Alice's side, but not at Bob's side. Bob has a Y that comes from the second independent quantum random number generator. So in this kind of scenario, one always assumes that the hypothetical local variable shared between Alice and Bob is independent of this alpha connecting Alice to her quantum random number generator, and of this beta, which connects Bob to his random number generator. So thinking of that, this NSI assumption, so no signaling and independence, is not really new. It was already there, but possibly a bit implicit in the old Bell inequality stories. Okay, now let's look again at that one. So this entanglement swapping situation. And here what we have is that it would be very easy for Alice and Charlie to always output 0. That's an easy instruction, just always output 0. Another easy instruction is always output 1. However, a convex combination of these two, so let's say half the time both output 0 and half the time both output 1, is not possible because Alice and Charlie don't share any common variable. They don't have shared randomness. Charlie has only lambda 2, Alice has only lambda 1. So the result is that the set of bilocal probabilities is not convex. And that's a huge change. And you can illustrate, I'm going to show that, but it also means that at the end, in some slice of the probability distribution space, you will get boundaries, so Bell-like inequalities, which are not represented by a hyperplane. So they are not represented in this two-dimensional slice by a line, but by these more complicated and non-convex curves. So let's maybe just do one example here. So again, let's assume that the inputs are binary, so 0 or 1, and the measurement results, I will label them plus or minus 1, just a notation. So what can now this alpha, before it was lambda 1, but the shared randomness between Alice and Bob. Well, this shared randomness has, together with the input X, determine the output. So this here has to be 2 bits that are labeled alpha 0 and alpha 1. So alpha 0 would label the output of Alice under the assumption X equals 0, and lambda 1 is the same, but for X equal 1. And now, giving all that, we can define these two quantities, I and J. So, some normalization, some sum. And you compute essentially some correlation between Alice and Charlie. But in this, for I, it is conditioned on Bob getting the input 0. While for J, it is for Bob getting the input 1. Okay. And now you define Q, the probability that alpha 0 is equal to alpha 1, so that these two are the same, so that Alice actually always outputs, that's the probability that Alice outputs the same bits irrespectively of X. And if you do that, then you can rewrite these expressions for I and J in function of this Q. Because, just some little algebra here. So if alpha 0 is equal to alpha 1, then this fraction is just 1. We call it, it's just equal to alpha 0. So I have my alpha 0 here. And in the other case, in the 1 minus Q probability case, so alpha 0 different from alpha 1, this just vanishes. And for J, it is just the opposite because you have the opposite sign here. Okay, so we get that. And doing that, we can actually now think of this 3-party scenario as a 2-party scenario. We put Alice and Bob together as 1 party with the input Y, so it's Bob's input, and the output is just Bob's output multiplied by alpha 0. And now on this 2-party scenario, we can run the usual CHSH expression or game, which is written here. And if you do that, you know that they will be, usually you have a 2 here, but I divided by 2 here, so that's the right-hand side is bounded by 1. And then you can compute that, and you can re-express that in terms of this I and J. And of course, you have also the Q, this probability that alpha 0 is equal to alpha 1 that comes into the game. And so if there exists a Q course, a probability, so between a number between 0 and 1 that satisfies this inequality, then we have B-locality. But in the other case, we don't have it. And we can then see that the existence of such a Q here, that's a little algebra that one can do, is exactly implies, or is equivalent, actually, that should really be an equivalent sign, to this inequality here. And you see that this inequality is nonlinear. Okay, you have absolute values, that's maybe not so interesting, but you have these square roots. And square root is clearly a nonlinear function. And that's why we get at the end this kind, it was on the previous. So the shape that you saw on the previous slide, which with the boundary were not straight lines. The boundary of the B-local set is not straight lines. So that's quite nice. And you can even prove now that all pairs of pure qubit states, so if I have a pure entangled qubit state here and a pure entangled qubit state here, then I would violate this inequality here. So this is at the same time nice, but you see also that it is very similar to CHSH. We really got all the inspiration from CHSH. So it's a first result, and it's always nice to have results, but it might not be the end of the story. And it is certainly not. Here you see again the shape here, which is clearly non-convex. Now you can also look what is the critical visibility to violate this inequality according to quantum predictions. And critical visibility is 1/2. So if you have a Werner state of 2 qubits, you can go down to, well, between Alice and Charlie, and after the entanglement swapping, you can go down to a visibility of 1/2, which is significantly lower than for CHSH, because you remember for CHSH, it's 1/√2. So if we do an experiment, an entanglement swapping experiment, and okay, it's a real experiment, so nothing is perfect, so we get a finite visibility, it will be much easier to violate this B-locality inequality rather than the usual CHSH inequality. However, this 1/2 means for 2 singlets, or for 2 Werner states. But now if we look at the critical visibility, okay, here is written per singlet, but what I really mean is per quantum state, and there are 2 of them. So per quantum state, it is 1/√2. So we recover again this 1/√2, which is precisely the critical visibility of CHSH. So you may also say this is disappointing, because I have made this assumption of independence, and at the end, I don't gain anything. Not good enough. And actually in my talk, I'm going to present many challenges. And I understand that at this conference, there are many students and maybe young postdocs. And maybe some of you are going to work on some of these challenges and maybe make some progress or find some solutions. And I would certainly be very interested if any of you make any progress on any of these challenges. So the first challenge would be to still look at this, what I call B-locality, which means really 2 locality, 2 sources, 2 independent sources. So in this B-local scenario, find a scenario maybe with more than 2 inputs, maybe more complex than the one I just presented here, which would allow a critical visibility per quantum state lower than the CHSH critical visibility. This is something that no one has found yet. But admittedly, if we go to quantum networks, the really interesting cases are not just on a line, but in a real network, we would imagine that we also have loops. And in a loop, okay, the simplest loop would be a triangle. So actually, you are going to spend quite some time now on the triangle or a triangle. So the idea is really we have Alice, Bob, and Charlie, and Alice and Bob are sharing some quantum state gamma here. Bob and Charlie are sharing some quantum state alpha, and Charlie, Alice, some quantum state beta, and they are independent. And John Bell would probably have loved that kind of scenario. So there's a first example of a triangle, so an example of that, which is kind of trivial, but it's already interesting, and that is due to Tobias Fritz. It again starts from this usual Bell inequality scenario with the two quantum random number generator here on the far left and far right of my picture. And then you take these two random number generator and you're going to put them together on top like that. And now here you have the two random number generators, so you get both the X and the Y outcome. Here you have this alpha, the one here, and Alice outputs X. So that's her inputs. She can always, of course, output her inputs. That's the easy part, and the same for Bob. But additionally, Alice also outputs, the usual outputs that she would get from her from her test of Bell inequalities, and Bob the same. So here we have typically a triangle, and obviously, if Alice Bob violate CHSH or any Bell inequality, we have an example of a triangle whose statistics cannot be reproduced by local variables. But you also understand that this is not really genuinely triangle. This is looking like a triangle. I mean, it is topologically a triangle, but it's only here that some interesting entanglement and interesting phenomena is happening. This alpha can be just a very classical variable. That's what happens when a quantum random number generator provides the inputs to Alice. This doesn't need to be a quantum communication. It can be just classical, and the same here. So actually, this is not really the kind of triangle we are looking for, although admittedly, this is the first example of a triangle, a quantum triangle that can be provenly not classical. Let's just look at that. So this is my triangle. And the question is really, is there a quantum case that cannot be done with local variables? Now I say 3 local because I have 3 sources, my alpha, beta, gamma. And notice here I have no longer any inputs. I have just measurements, fixed measurements, defined once forever. And Alice, Bob, and Charlie, they perform their measurements. They get, of course, outcomes. And so we have a P of ABC, and the question is whether this P of ABC can be simulated in this 3 local way with 3 independent local sources. And maybe even before answering that, there's another question. Can these local variables be discrete, or do we need to go to a continuum? And if it can be discrete, can it be finite? And how many symbols do you need to do that? You can look at an example. Let's suppose alpha, beta, gamma are uniformly distributed in the unit interval, and that the outcome for Alice is 1 if and only if beta is larger or equal to gamma, and similarly for Bob and Charlie. And with this example, which is clearly a local example, we get that actually the probability that A equal B equal C is 0, because the probability that beta is larger than gamma and gamma larger than alpha and alpha larger than beta, this is 0. And all of our possibilities are equally likely. And this here is an example where we have a continuous infinity of values for alpha, beta, gamma. Can you do that also with discrete number of variables, or possibly even finite? When I first looked at that, I thought I had a proof that this is impossible. And indeed, it is impossible with finite alphabets if you assume identical response functions. So that Alice response, of course, has to be a function of beta and gamma. And if you assume that the response function for Alice is the same as for Bob and the same as for Charlie, which is very natural because the entire problem is completely symmetric. But if you make this assumption, then you can prove that this is impossible to reproduce. However, then with Denis Rosset, we could prove that if you have different output functions, then you can do it. You can do it with finite alphabets. And so with Denis Rosset here again, we could prove that actually if the outcomes here are binary, then an alphabet of 6 letters will always be sufficient. I'm not saying that 6 letters is always necessary. Maybe you can do it with less than 6, but for sure, If it is local, then 6 letters are sufficient. So that helps. You can start thinking of even going to a computer and so on. I have to say also, if instead of having binary outcomes, you would have outcomes of from an alphabet with 4 letters, which is very natural if you think in terms of qubits, because when this Hilbert space would be of dimension 4, then this 6 goes up to 64. So the number of letters grows very fast. Anyway, so the question is now, okay, we have this kind of triangle or network, and we want to understand how to characterize such a distribution such that it satisfies this NSI principle. So we really have a kind of little, so I find it very fascinating for the following reasons. We have really 6 qubits. Just let's suppose we go to the simplest case. So it's qubits. So we have 6 qubits. So it's a 6-qubit toy universe. There are no inputs. And everybody does perform some quantum measurement, but some fixed given quantum measurements. And we ask a very simple question. Now we want to prove that the outcomes are really quantum, so that this entire triangle has some quantumness, and in particular that the outcomes contain some randomness. It's a very natural question. And look, here we would get randomness, as we already have with Bell inequalities, but we would get randomness out without any input, so without providing randomness in. In Bell inequality, you put randomness in, you get more out than you put in. Here we put nothing in, no inputs. Still, we expect to get some randomness out. And because I said randomness, let me now open a little bracket just for a couple of slides on quantum technology, because I find that also fascinating. So you know that quantum randomness, you can also just think of a beam splitter, a light source, and then you have 2 detectors, one you label 0, one you label 1, and you get a string of bits, of random bits, and you can put it into these little boxes. And okay, that's one thing that the company IDQ that Aaron was mentioning in the introduction is commercializing. But the IDQ engineers recently have been able to put essentially all that into a little chip, which is really millimeter size, and very importantly also has really microwatt power, so very low power consumption. And once you have this chip, you can put it here into a smartphone, which in this example is a Samsung smartphone. And then you have okay, do you want to call it a quantum smartphone? At least you have something which is really quantum in it. Of course, it's only a quantum random number generator, but still that's interesting. Now, what can you do with it? Well, you need an app that is using it, and there are apps indeed. So for instance, this mobile banking application here that really uses the quantum randomness to secure the communication, the transaction, and I don't know exactly what. Okay, so I have also to admit that for the time being, you can buy this only in Korea from Samsung. And actually very recently, you can also buy it from WinSmart in Vietnam. So there's a second company in Vietnam also producing these quantum smartphones. But I don't think you can buy it in India. For sure, you cannot buy it in Europe today. But hopefully in a few, I don't know, years, months, we'll be able to have a quantum device in our pockets. Okay, so let's close this bracket and come back to quantum entanglement science, which is really the subject of today. So we have this triangle, and we want to formalize this principle of NSI, no signaling and independence. But how are we going to do that? Remember, we have access only to PABC. So for instance, no signaling usually means that Alice's local statistics will not depend on Bob's input or on Charlie's input. But there are no inputs here, so that's not a good approach to characterize no signaling. And also independence, how are we going to do that? Yeah, that's what I just said. There are no inputs. So how are we going to do that? Well, actually, there is one trick that we're going to use. You know, if we just think now Alice, Bob, Charlie, just look at the bottom here, Bob, Charlie. they are in this configuration, but it could be that actually Alice at a distance decides not to perform any measurements, but decides to change the local topology. And that should not affect the Bob-Charlie correlation. That is no signaling. Here is an example. So Alice invited a friend, Dave, to join. And now we have a square, as you see. But from Bob and Charlie's point of view, Bob still gets this gamma, so still connected to the source gamma. Of course, between Bob and Charlie, there's still the source alpha, and Bob still receives information or quantum stuff from a source beta. And we, of course, still have to output, okay, a bit, or maybe it could be more than a bit. And so the Bob-Charlie correlation should remain the same whether we have a triangle or this kind of square. And moreover, in a square, Alice and Charlie now, they are not connected at all. So Alice, Charlie should be independent. So their statistics, if I trace over Bob and Dave, I only keep Alice and Charlie, I should get some probabilities that factorize. And the same, of course, for Bob and Dave. So now here we have no signaling and independence. And this is NSI. Let's look into that a bit more. But the first thing, so what are we going to put here? So here the source is already there, that's clear. What can I put here? Let's make the assumption that we have just non-local boxes everywhere. The most powerful, but still independent. And then I can just put the most powerful source also here. And let's also start for simplicity with the case that the outputs are just binary. And I still label the output plus or minus 1. And I'm going to make also the assumption that locally we just have randomness. So everyone, the single party outcome are random, which means the expectation value is 0. Now also make the assumption that all these two-party sources, NSI boxes are equivalent. So all the connected two-party correlations are identical, and I just call this E2. Now, because of this no signaling, the E2 of the square should be the same as the E2 of the triangle. So if I can bound the E2 square, I'm bounding the E2 of the triangle. And then, okay, for 3 connected parties, I get an E3. And because of this independence, as I said, Alice, Charlie, they are independent, which means that their expectation value of the product of their outcomes is 0, and the same for Bob and Dave. Okay, so it means that now this P of A, B, C, D can always be written as, okay, some normalization, 1 plus, the connected two parties with an E2, the 3 connected parties with E3, and the 4 parties. So this is fully general. There's no assumption herein except what is written here already. So E1, 0, equality, and this independence here. Now let's apply that to these possible outcomes. Outcome plus, minus, plus, minus. Okay, you compute, you get that, and just a straightforward computation from that. And this obviously has to be non-negative because it's a probability. And now you do elementary algebra and you get as a conclusion that E2 has to be smaller or equal to 1/2. So you get some constraint on the two-party correlators. And you see this, okay, here is a very simple example with just going to a square. We can go then to hexagons or more complicated schemes. But you see and you understand, hopefully, that you get some constraints on the correlator, the two-party correlator. And again, because of no signaling, this is the same as the E2 of the triangle. So we made some progress, and you find it in this paper, for instance. Okay, now if you go all the way to an hexagon, so here you double every source, so you don't need to make these assumptions about identical sources. Let's suppose first that we also impose E1 equals 0, so single party output pure randomness. Then you get this bound E2 smaller equal to square root of 2 minus 1. So you get a better bound than the 1/2 I had before. maybe before I continue, just want to make sure, because there is absolutely no noise. Are you still with me? Are you still hearing me and following the presentation?
Yes.
Okay, good, thank you. So let me continue. And you can, look really more into that. And for instance, plot here, E2 in function of E3. And you will get, of course, some bounds just from the positivity. So for instance, this bound is just the positivity of the result plus, 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 cannot be negative, and so on. But here you have this result, which is presented here on top, that the E2 cannot be larger than this, 41%, which corresponds to square root of 2 minus 1. So that's all nice. And we also could find local models almost everywhere here, except in this little region. There's a small region here where we don't know. Maybe this is local, maybe this is quantum, maybe not. We just don't know. And so a second challenge would be to really investigate this source and find out whether here we have a quantum distribution, a local distribution, or local but not quantum. No, that cannot be quantum but not local, or neither local nor quantum. We just don't know. Continuing with this here, we could also find some explicit inequalities. Not going to go into the details. Again, you find it here. But important is, again, you see that you get some non-linearity. And we were expecting, of course, non-linearities here. And you get indeed these. So this is under the assumption that the marginals, single-party marginals, vanish. In full generality, the inequality is even a bit more complicated. So you get something here. Could still ask, can this be violated quantum mechanically? Still an open question. Now, there's one thing in all these inequalities. So again, let me look at that. So I find this quite remarkable. So I'm quite happy with these kind of things. And it involves the single party marginals, the two party marginals, right here you see, for instance. But this way of deriving inequalities will never involve the free party that appear in the triangle, the ABC of the triangle, because we open the triangle, and by opening the triangle, we break the free party correlator. And so I don't know how to derive NSI inequalities that would really involve free party correlators. Have not the slightest idea how to do that. I guess there must be a way, because of course in a triangle, free party correlators must be important, but I have no idea how to do that. So this is my third challenge for all the youngsters in India and elsewhere. But now let's go to maybe the more, let's say, closer to quantum triangle, where the number of outputs is 4. And again, this is just because if we imagine that we have a 2-qubit source here, a 2-qubit source here, it means that Charlie, like all the others, receive 2 qubits. So they have a 4-dimensional Hilbert space. And so it is natural, it's not necessary, but it is natural to assume that they have 4 outcomes, 1 out of 4 outcomes, and the same for Alice and Bob. And now if you look at that, you say, okay, there's one thing which is obvious to look at. Let's suppose we have Bell states here, for instance, this phi plus state, or take the singlet, and everybody just performs a Bell state measurement. That you can do, and you will get, of course, a P of ABC. However, this P of ABC is local. It happens to be local. So somehow, by just doing Bell states and Bell state measurements, you cannot prove any quantumness or any quantum randomness in this triangle scenario. So you need something else. And so you can ask yourself, what is a natural 2-qubit measurement? Not one that does a measurement on one and a separate measurement on the other one, something which is a kind of entangled or coherent 2-qubit measurement. Of course, every student would first say a Bell state measurement, but that's not good enough. We need another one. So here's another one, and I don't think there are many. I think this is essentially the only alternative. And I call it the elegant joint measurement because I think it's quite elegant. So here represents the block sphere and a tetrahedron in it with the 4 vertices, M1 to M4. And I'm going to look for an entangled state of this Mj minus Mj superposed with minus Mj and Mj. Of course, this means really is the ket corresponding to the state minus Mj, tensor product with the Mj state. And the coefficients here, the C0 and Q0, I'm going to compute them by imposing that these states are mutually orthogonal so that they form a basis. And notice also I have assumed that these coefficients do not depend on J. It should be the same for all of them because I want some symmetry. And then you get these numbers here. So it's not a too complicated computation. You get that number. And okay, if you insist that these are real numbers, this is a unique solution. And with that, you can now see that the partial, so the local states will point in the direction of the tetrahedron, of the vertices of the tetrahedron, with this reduction factor, square root of 3 divided by 2. Okay, so this is a kind of, okay, I find it elegant and very natural. Okay, I introduced that in this paper. And if now you assume, oh yeah, here is an additional challenge. So here this is all done for qubits. But there should be a way also to have this kind of measurements in higher dimension. For Bell state measurements, we have it also in higher dimensions. Can we have that here also in higher dimensions? And so possibly for more parties, not only for 2 parties. Again, here, I don't know how to do that. And if anyone has an idea how to do it or can do it, I would be very interested in seeing the result. So let's now come back to our triangle and say everyone does this elegant joint measurement and they share a singlet. What comes out of straightforward computation is that the probability of getting result A, B, C is quite high if A equal B equal C. Of course, there are 3 possibilities. They could all, or 4 possibilities. They could all be equal to 1, or all to 2, all to 3, all to 4. Now, on the other side, having 2 of them equal and the third one different is very low. And then the rest goes to the case where all the 3 values are different. So here we see that it's quite a remarkable distribution because everyone being equal has a large probability, while 2 being equal but not the third one is very small, not 0, but very small. And then this is a distribution. This is a quantum one, because I told you how to do these quantum measurements and the quantum states. But is that one local or non-local? We don't know. There is no proof today. This is again an open problem. I think it's a difficult question, but I think it's a very fascinating one. And in general, if you have PABC and you assume that you have this invariance on the output permutation, if you permute, now the output is 0, 1, 2, 3. If you permute these outcomes, of course, that doesn't change. If you output these, permute the outcomes, it's not going to change these conditions. And you have a normalization, so you have 3 variables plus normalization. It means you can represent everything in terms of let me go a bit faster here, in terms of a plane, of a slice. And in this, with some conventions of what I call now correlators E2 and E3, you get it like this, and you then get that in this plane, you have, of course, again, boundary conditions here. My pointer moves a bit slowly, but okay, which corresponds here to P1 being non-negative and so on. Here at the origin, that would be pure noise. Of course, pure noise can also be done. The elegant joint measurement result corresponds to this point here. And if you had the noisy singlets, you could go continuously from that one all the way down to here. And maybe one interesting question here again is the following one. Are there any other points in this 2-dimensional slice? So quantum distribution, which is invariant on the output permutation. which is different from just the elegant joint measurement mixed with noise along this red line here that you see. I tried to find any, and at least numerically with qubits, it seems impossible, but I have no proof. And not only do I have no proof, I have no idea how one could prove that. So ideas are needed to prove this. And even if you prove it for qubits, then the question would remain for higher dimensional quantum system. Of course, higher dimensional, but still limited to 4 outcomes and invariant on the output permutation. Okay, I don't know if I want to go into that. Tell me, Aaron, how much time do I have now? Because it's already 10 to 5, so maybe I should speed up.
Yeah, so we are now 8:20, so maybe another 10 minutes we have.
Okay, good. Thank you. So there is a related problem that people in computer science have studied. You know, they want to know, are we in this kind of scenario with a common source? We don't speak in terms of quantum sources, but just a quantum, a central source computer connected to ABC, or is it more like that, like the one that we are interested in? And they could find some inequality here, the classical inequality. So this inequality cannot be, that is for the GHZ, so for this network, and for our triangle network, they get this kind of inequality, which is written here, and which I'm not going to explain here because of the lack of time, but this is a classical inequality. And sorry? And what we could find is that this FINA, it's called a FINA inequality, and this FINA inequality actually also holds quantum mechanically and actually also for PR boxes and some wiring. Okay, and here this FINA inequality, so my pointer is moving very slowly. So this FINA inequality corresponds to this kind of, which color is that? Kind of green line here. So clearly it does not exclude the elegant joint measurement, which we know because the inequality is satisfied by quantum predictions. So it's clear that nothing here can be quantum. Everything which is on the top right here of this triangle is excluded by the FINA inequality. But we would like to move closer to this elegant joint measurement distribution. And one thing, because doing this computation, now we have 4 outcomes. So with local variables, it's 64 variables per source. We have 3 sources, so it's a lot of variables. So it's difficult to do a simulation, even numerical simulation. So what we tried is to go to machine learning and these neural networks, these kind of things, where it is actually quite natural. You would have 3 neural networks, and the 2 first are connected to one source gamma. The 2 last ones are connected to a source, source alpha, and the first and last one are connected to a source beta. And then you can let this neural network run and try to see if you can simulate this elegant distribution. This was done by the student Tamas Krivashi. And the result, okay, let's not go into all the details. Essentially, the result is shown here. So this in colors is what you get as local models. And so here what you have here horizontally is, let's say, the visibility. So one would be pure singlets. And for pure singlets, the distance between the best local model found by these neural networks and the quantum distribution is high. So clearly, the machine is giving a strong indication that this is not local. But it's not a proof. It's just an indication. On the other side, if you have pure noise, then the machine tells you, yes, here we have a local model. That's pretty obvious. And here, so what this indicates is that there should be some non-locality and so some quantum randomness in this, but only up to some visibility, like, I don't know, 85%, something like that. We don't know exactly. But of course, this is just, again, a numerical simulation, but at least it helps to guide. Now, what we also did is to make some assumptions. Assume all sources and all response functions are identical. I would say that's a reasonable assumption, but we made also the very strong assumption that all the response functions are symmetric. So A is a function of beta gamma, and we assume that it's a function beta gamma or gamma beta. It is invariant. And then with that assumption, we could get that this is the boundary of the local set. So this would be for sure local. And outside is not local, but not local under the assumption of symmetric response functions. So it's not yet good enough, but that's the best result we got on that so far. But now let me continue with another example, which now is indeed where I have a proof. So it is maybe not as natural. You will see that it's a bit a construction that is made for the purpose, but it achieves the purpose. So it's nice. So here again, we have Alice, Bob, and Charlie, 4 outcomes and variables alpha, beta, gamma. And let's assume first that the measurements, so first all the sources, the quantum sources are phi plus, or Bell state. And the measurements, Alice, Bob, and Charlie, are all the same, so that's nice. And they have 4 eigenstates, of course. And 2 of these eigenstates, phi 1 and phi 2, are just product states. So phi 1 is 0, 1, tensor product 0 times 1, qubit 0 times qubit 2, state 1. And for phi 2, it is just the opposite, 1, 0. And the 2 of us, phi 3 and 4, are superpositions of 0, 0, 1, 1. And actually, okay, with these coefficients, of course, the coefficients have to be such that they are mutually orthogonal and normalized. So the C, you can think of it as a cosine, and S for the sinus. And then the first thing you see is that if you have 0, 1, 0, 1, so to get twice the first outcome, let's say Alice gets 0, 1, so she gets a 0 from beta and a 1 from gamma. But if there is a 1 here, and this state is a phi plus, there cannot be a 1 here. No, sorry. If there is a 1 here, there has to be a 1 here. So if there cannot be 0, 1, and again a 0 here. So you get these very strong constraints, and that's why this measurement was really cleverly chosen, such that these kind of probabilities vanish. And once you have some vanishing probabilities, it helps a lot in these kind of games to rule out local models. And this is really an idea due to Salman Beji, who is a professor of computer science in Tehran, in Iran. And he worked a lot with Olivier Renou, a student we had in Geneva, but he also visited Salman Beji in, here is Salman Beji, in Tehran. Okay, so because we have this, we can now make some proofs. And we have a theorem. I'm going just to hint a bit how we come to this theorem, but the theorem says that if this C1 here, this coefficient here, is large enough, then the quantum distribution is indeed non-local. So you cannot describe it as a probability distribution over local variables. And here again, you see the independence assumption. You have products of probability distributions, and then Alice output depends only on beta gamma, Bob on gamma alpha, and C on alpha beta. So that's the theorem that you find in this paper here. And the idea of the proof is that it goes in two lemmas. First, because of this 0 in the probability distribution, which I mentioned here, this 0 here, this gives you a lot of structure. And this allows us to actually prove that the sets of local variables, so that's x, y, z, which are the local variables. So x is the set of alphas, y is the set of betas, and z is the set of gammas. These sets partition in two subsets, which are disjoint and whose union is equal to the full set. And actually, it does it in the following way. So for instance, the results on Alice will be the first, corresponding to the first eigenstate, if and only if beta belongs to y0 and gamma to z1. So you can use that as a definition actually of Y0 and Z1 and so on. And then you can prove that they are indeed disjoint and that the union is the full union. Okay, so that's the first thing. And this one is really exploiting a lot the structure of this special measurement, this here. And then you have a second lemma, which is really somehow more easy because this is really essentially linear programming. When you have to find out what is the maximum value of C1, this coefficient here, in order for a local model to exist. And you find a very strange number, by the way. You get this number where K is equal to this strange number. So why these strange numbers come up here is not very clear to me, but that comes out. That's just a result of some computation. And so for C larger, again, from that, you cannot have a local model. Of course, for C1 equal 1, you would again get a local model because then this becomes a product state. But C1 in between this strange model and 1, you have no local model. Now, this is very nice, but this is really exploiting this equality to 0 here. And so as soon as you would add some noise, let's suppose we want to do an experiment, or just to be a bit more realistic, we would like to have some noise resistance. The problem is as soon as you add some noise, you no longer have equal 0 here. You may have a small number, but not equal 0. And so to prove that this distribution, which often I call the Salmon distribution, is noise resistant, is my next challenge to you guys. We also studied with this machine learning stuff, these neural networks, and we changed. Okay, now this here should be C squared. It's really the C that we had before that starts here, exactly here with this, and here it is the square, while here, sorry, here it was not the square. But if you take the square of that, you will get 0.7 something. So we are here. And we do indeed find that the distance to the best local model found by our neural network becomes larger here in this region. So at 1, it is local. Here, actually, we have a local model. Here it is would be a maximally entangled state, these eigenstates. And so here we also have a local model. But what the machine, the neural network tells us is that actually there's seemingly also some non-locality in this region below this critical point. And so this is again an indication. So here we have a proof. Here we have an indication, but no proof. So of course, the next challenge will be to prove that this Salmon distribution is also non-local in this region. And again, it's a question for which I have no idea how to solve it. And maybe here one more. We started with really the idea that we have this triangle and we want it to be genuine triangle. We don't want to cheat. Essentially, I guess by genuine triangle, we mean that it cannot be done. You cannot do it if you have only 1 or 2 entangled states. You really need that all the 3 states appearing in this triangle are entangled. So we would like really also to define even what we mean by genuine triangle. Probably we need that every state has to be entangled and every measurement should have at least some entangled eigenstates. But is that the right definition, the best definition, the most productive definition? I don't know. Okay, so I come to my conclusion. Okay, here is a summary of some of the challenges, not all of them, and some of the papers, also not all of them, but you find more in the slides, and I guess you will have access to all that. And really the thing which I think is still a bit missing is to be able to prove in a device-independent way the existence of randomness without inputs, and really moving away just from a folded CHSH where you just put the quantum random number generator together, this Tobias Fitts example of a triangle. But in a genuine triangle, without inputs, prove the existence of quantum randomness. Okay, thank you very much. I hope you are still all there.
Yeah, we are here.
And if you have questions, I'm certainly open to spend some time trying to answer them.
Yeah, so yeah, thanks for your very intriguing talk and very nice and exposure to this recent developments. So we have a couple of questions. So should I tell them they can ask directly, or should I read? Or you can also read in chat box and try to reply.
You have to read at least the question which is given in YouTube.
Yeah, okay. So there is one question from Manik Banik. He says, is not the source independence assumption used here is similar to preparation independence assumption used in the Ushe-Bharat-Rudolph theorem, PBR theorem? Is it same or is it different?
Sorry, I didn't get the question. Maybe how can I get?
So the question is not the source independence assumption that you are using here similar to preparation independence assumption that PBR have used in their theorem?
Similar to what? To what kind of? Let me stop share. Well, I don't know. Maybe.
If you stop sharing, you can see the chat box. Yes.
So where is this chat now? I think I have too many
You
things.
can see
On
the
my
chat
screen.
and
Lost here. Or is it maybe here?
Yeah, next to the share screen option.
yeah, below you see the participant and chat. There you click.
Ah, chat here. Yeah.
Yeah, you see a question from YouTube. So question was asked by Manik Banik.
Ah, okay. Now I see here. Yes. So I guess indeed, if you just go to this kind of scenario where you have, where is that? Yeah, this one. We put that on the side. So in this kind of scenario, indeed, the measurement independence assumption, which is also sometimes called this freedom of choice, is equivalent to independence assumption in my scenario. However, of course, as soon as you go to maybe longer chains, not just 1, 2, 3, 4, you could have 5, 6, whatever longer, or as soon as you have a loop, then this NSI assumption is really different and goes beyond just freedom of choice. But indeed, it is inspired from this, or at least, yeah, as I say here, I mean, Bell inequality, maybe I say it in the previous slide. Anyway, it is very much inspired from the, yeah, it is implicitly assumed in Bell tests with, okay, here I say random number generator, I could have said with the assumption of measurement independence. Yes, correct.
Okay, so there is one more question by Ujjwal. Maybe Ujjwal, we can ask.
So
hello, Nicolas.
See it here?
Hello.
Hello.
Hi. Yeah, so I just wanted to ask the following, that if you are in higher than 2 qubits, but still bipartite, there is this early paper where it was shown that the maximally entangled state does not violate the Bell inequality, the 3x3 Bell inequality maximum. So now if you go to the network, but still work with two-party things, do you see a similar thing already for qubits?
Okay, I don't know. So the fair answer is I don't know. For sure, here with this kind of, you can always do it. So you will at least do as well as in Bell inequality scenarios, because you can just map it to here. But maybe in this NSI frame, you can do better. And could you, for instance, do what you said with qubits? I don't know. And you can ask the same question for Q-treats. Would it? There might be also cases where for Q-treats it is actually more natural to think in terms of maximal violation for the maximally entangled state. But again, I don't know. The fact is there are indeed many open questions here, and so maybe it's nice for students to work on them. The thing that people should also remember is really because of this, where do I say that? Because it is not convex. No, it's somewhere. Where do I say it's not convex? Yeah. Because of this non-convexity here, that makes the problem difficult.
Yes.
And so one should not be surprised if working on that is hard. It is, so if you want an easy problem, go for Bell inequality. That's easy. Here it is much more difficult, but I also think it's much more interesting and more timely. We have played with Bell inequalities for decades, and I think we understand that. So it's time to move to these network Bell inequalities, but we have also to warn everyone that this is difficult.
Yes, yes. So for this Salmon triangle, you showed that when C1 increases, you get a better result. So that C1 increases means it's going close to 1 over root 2 or is going beyond that?
No. It's not even reaching 1 over. So this, no. Let me see. I guess you are referring to this here. So so 1 over square root 2 is here because remember this is the square. So the square of 1 over square root of 2, this is 1/2. So this is maximally entangled. And our proof starts to work only here. About 75% or 74% here. And here oops, now I'm moving this cursor. Okay, here we have the proof, the analytic proof of non-locality. And indeed, what these numerical simulations show that there seem to be larger non-locality here in the sense that the distance between the best local model and the quantum model is larger. And when that goes down to 0 here, that's normal because here we have a local model. Here on the other side, okay, here you don't see it, but you have this even larger peak. And this is a numerical result again. And whether this corresponds to something correct or not is again an open question. I just don't know. I'm afraid in this talk, I very often told you I don't know, just because the fact is that I don't know.
Yes, of course. But if we can analytically prove this result, then that would show that increasing entanglement is not good. I mean, you get a better result at a lower entanglement, right?
Exactly. It could very well be. At least there is no monotonic relation.
Okay. Yeah. Thank you very much.
So there is one more question by Shiladitya Mal. So Shiladitya, would you like to ask the question yourself?
Yes, I can ask.
Yes. Yeah.
Okay. First one, thank you for the enlightening talk. I just asked you, when you talk about Bell inequality without input, that means there is no requirement for randomly changing the settings. So
Correct.
without that requirement means we can drop the assumption of freedom of choice. So do you think the assumption of independence is invalidated, the assumption of freedom choice required?
Yes, I think there is something like that. So indeed, see, in this triangle, you have no inputs. Of course, it doesn't make sense to talk about freedom of choice. However, there is the assumption that I have, I hope, emphasized enough, that we make the assumption that these hypothetical local variables, alpha, beta, gamma, are independent. And you see it here, their probability distribution factorizes here in these three terms. This is a product here, this is a product here. So making this assumption gets rid of this freedom of choice, which anyway, freedom of choice is also a very loaded terminology. And what we really mean by that is independence. And here I think we are formalizing this independence assumption in a very natural way. Again, think that this source here is maybe a solar, powered by solar panels. This one is nuclear power. This one is someone on his bicycle. So it's very natural to assume that these are independent. It's not a matter of choosing. It's just that they are independent. They are maybe also independent just because they are very far away from each other. but it is an assumption.
Yes, yes. That means that this assumption actually does not require the randomly changing settings. So that assumption, so it is in that way. One assumption replaces the another assumption. Can I say in this way?
Yeah. Yes. Yes.
Thank you. Thank you.
Welcome.
So there is a last question by someone. He asked.
That you can skip because I think this one never discussed by Nicolas.
Yeah, I think outside your your talk. So yeah, you can skip that. So okay, so there are no more questions. So let's thank Professor Gisin once more. So
I'll encourage you all to work on my challenges.
yes, yeah. So very inspiring. So I hope many students will take interest in your talk, in your challenges. So
very good. Thank you very much.
So before you leave, can you step online? We would like to take a picture with everyone on the screen, like like
So
group
let
photo.
me stop sharing here.
Yeah. Stop sharing and then we take a picture. Yes.
Okay.
So please, everyone can actually start video and we quickly take a picture.
Yeah, please switch on your video.
Yeah. So Ganesh, could you please take it?
Yeah. Once everyone. Sohail, Riddhi.
Ribhu is there or?
Where is Riddhi?
Yeah. Some people
Yes,
have.
ma'am. I'm here.
Yeah, but your video is.
How many people do you have on your screen? One, two,
About 40.
40 around.
25. But,
yeah, we have to take several so that. So, Ganesh, we are ready.
Yes. 3, 2, 1. Say cheese.
So virtual group photo.
Say cheese again. Thank you. That's nice.
okay.
Thank you very much.
After the presentation, I'm going to have some Indian tea.
Oh.
Thank you.
Thank you, Professor Gisin.
Thanks. Yeah, for finding time. So yeah, thank you.
Bye-bye.
Bye. Yes.
So, I think we somehow ending our officially Young Quantum 2020. So I request Ahona and Kornikar to give vote of thanks. So,
Yes. Can you hear me?
yes, clear.
Okay. Hello everyone. I am Ahona and with Kornikar, it is a privilege for us to have been asked to present a vote of thanks for this event. Due to the ongoing pandemic, Young Quantum 2020 had to be held online and we were not able to meet in person. In spite of that, with the huge effort and cooperation from everyone, I think we can say that the event has been a great success. As Professor Pinaki Majumdar noted in his inaugural speech, we would like to believe that this is also a small way in which we fight the virus. I, on behalf of the Harish Chandra Research Institute and the entire fraternity and sorority of people here, would like to extend a very hearty gratitude to all the participants, poster presenters, speakers, and keynote speakers for presenting and discussing their works and sharing their opinions with us. I convey my heartiest thanks to all the chairpersons for their very enthusiastic participation and valuable suggestions. We are very thankful to the moderators for their crucial support in providing the coordination between Zoom and YouTube, the two online platforms on which the event was held. And let us not forget to thank Zoom and YouTube for that. So, I think...
Am I audible?
Yes, you are audible.
I am Kornikar. And what
Muted. Kornikar, you are muted.
who always I would like to thank all the members of the computer section who always extended the technical. We would like to mention that in this program, we have had a relatively good ratio between male and female participants, and the ratio is 5:2 approximately. And there has been 2 female speakers and 15 female poster presenters. This selection was made according to a uniform criterion, and we hope that in the next YouCube, we will have a larger number of female speakers. I would like to convey my deep thanks to our director, Professor Pinaki Mujumdar, for his support and valuable suggestions. I especially convey my thanks to all officials of the administrative wing of HRI for rendering us with very useful support. I would like to extend my sincere thanks to DAE for their cooperation and continuous support. I would like to express our deep gratitude to the faculty members of the QIC group for their valuable suggestions for organizing the conference. Finally, I convey my thanks to all the members of our QIC group for taking the initiative in organizing the event, and especially Brij Mohan, Ganesh, and Ribhu for their huge enthusiasm. Thank you all.
So let's clap. So unmute and clap, everyone.
Yes, I think we end YouQ 2020, and we hope that next YouQ will be at HRI, and we will see all of you at HRI. And so hope for the best. Take care, stay healthy and safe.
Okay, so
Bye-bye.
bye. Take care. Yeah.